Advantages of differential signaling. First that you can do is, if your signal is carrying a single line, right, and there is noise on that line, you get that single line also will have influence of the line. For example, you have a line or a trace here. This trace is having a buffer and it is carrying a clock signal, right? Right. So you'll have a clock signal like this. Now, just in case that you have your amplifier signal going next to it, right? If this is your trace, then what will you see? This amplifier signal, if you are giving a sinusoid input, you will see that the output being like this, but you can also see every time when there is a peak signal, you will also see peak graphs in this. Right? So this is called noise. This is the switching noise. Switching noise of a clock, or it is also called coupling, signal coupling. Other terms you would use, this would be the aggressor and this would be the victim. So the changes in the aggressor are getting impacted in the victim. So there is some signal coupling happening. Now this one is called environmental noise. So what differential signaling would give you is, it would give you immunity to environmental noise. How is that? How do you get immunity? The best way of doing that is if you have a differential signaling, meaning if you have a clock source going in this direction with a clock output, and if you have a coupling, you know that there is going to be coupling on both sides. So this is V in 1, V in 2. Now if you get the clock in one direction like this, this is going to be the clock signal, and you have the clock in the opposite direction here. And if you see that the edges are going to be equally present on both sides. Right? But if you take the difference between the two, these two will cancel, the edges will cancel with each other, and you will get a clean signal. So this means there is going to be an immunity to environment noise. So what are the sources of these? The sources of the noise can be in the coupling. You have got capacitive coupling. Okay, you can couple capacitively, or you can inductively. You can be coupled. Okay, you generally do not see resistive coupling between the two lines that you have. So what you can do is, if you want to make it immune, you can have the differential signal on either side, and that the aggressor which is present here will affect both the victims uniformly, and these victims when they subtract with each other and the transition, the difference between the two is intact. So V in 2 minus V in 1 will be intact. No noise in present in them. So this is one good advantage of differential signaling. Likewise, and the same thing, if you have any noise here in the power supply, this is also going to affect you in some form like this. So you will also have likewise immunity to supply noise. Right? So whatever the change is there, you will see. For example, if there is a change, this change, if you can call it as say VDD plus delta X, and this is VDD plus delta V will have delta V. Right? So this would get affected by V out plus delta V. Here, since it is going in the opposite direction, V out minus delta V. So the difference between the two would be V out only, right? So that will be, the difference will go away. The noise difference will go away, the supply noise difference will go away, and you will get this. So it is immune to supply noise, community noise. Next is in this particular case, if you have, now that we have seen one aggressor and two victims, what will happen if you have two aggressors and one victim, right? For example, this is going to be very common when you're doing high-speed signaling. So this is one clock signal. Right? And second, you have another clock signal. Okay. Now, if you observe, the clocks are differential to each other. Clock 2 and clock 1. Now, in between them, if you have a high-speed analog signal passing through it, then both will impact each other. So this is going to be a signal that is coming. Then the noise will get coupled from this to this circuit, this one to here. Both will get, so this is called noise coupling. Right? When you have this here, the differential, because it is differential, the coupling will be reduced due to the consequences. So what you can do is you can only reduce the noise coupling. You cannot eliminate it, but you can significantly reduce the noise. So how is that? Suppose you have, this is called line L1. Okay. This is line L2. This is line L3. This is line L1. So typically now that they are going in opposite direction, this noise coupling will be delta V. And this noise coupling, if it becomes minus delta V, delta V and minus delta V will cancel on L1 and you will get the output. So noise coupled from L2 to L1 and L3 to L1 will cancel each other. Okay, note 100% cancelling cannot happen. from calculate. Another thing what will happen is, since you have heard about these two, then because of their noise coupling, you will see that these are sensitive to common mode level. Common mode level. So in case your common modes for these two circuits are different, then your common mode level can either take you up or down. What is the best way of showing this example is, suppose you have now two signals. One signal is this way, the other signal is this way. Okay. So this is signal 1, signal 2, and they have a common mode level like this. Now, if the common mode level is optimal, what will happen? These two will amplify. Okay. These two will amplify when their graph is with respect to time. Now, what happens if this common mode level shifts upwards? If the common mode level shift upwards, same graph will now start looking like this. This is called clipping. So common mode will start clipping and you will see saturation in the signal. You will not be able to understand what is happening. Suppose common mode shifts downwards. Now that you have seen, this is going upwards. What happens when you go downwards? If the common mode moves downwards, the graph will now start to clip below. Okay. So now these differential signals are very sensitive to this. So what do? You have a challenge here. What is the challenge? The challenge that you will identify is, if your V in common mode signal either goes up or goes down unreasonably, then you will see clipping. Okay. So what do? You do is, this is the, so what do you do? A solution. The solution is, you add a feedback circuit. Feedback circuit such that you measure the output. Measure the output values. Okay. Then you sum the value, then take reference, appropriate reference, and then feedback to the common mode point. Okay. Common mode point, you feedback, and this is going to be tuning it. You tune the common mode appropriately to either go up or go down, such that, what is the aim? No clipping. So this loop feedback is called common mode feedback circuit.